And in order to do this, since this is going to be quite technical, I want to talk about where he comes from. And Andreas did this yesterday in the beginning of his talk, and today I'm going to give a very practical example of a fully worked out base case for Goodstein. The reason why we do this is because there is a script that Goodstein has to follow in order to conquer any other theory, and this script is the same as for the original result. It's the same as for going from ATR0, for going for ID1, for ID2, and modulo a lot of technicalities. So in a sense, the plan is already set. And in order to have this plan in mind, we are going to go through the base case. So we saw these days what are the ingredients for defining a Goodstein process. So we have to start with ingredients. So you need a notation system for your natural numbers. And for the base case, well, we know how to write natural numbers, so I'm going to pick a number m equals to 4. The second component is a notion of normal form representation. And for the natural numbers, this element is the exponentiation. So normal form representation. And so the way that we do this for the natural numbers is to write for picking a base bigger than, at least as big as 2, and writing this as 2 to the 2. Now, there are two options here. Either you write, say we have 16, and this is 2 to the 4. Either you stop here, and this is your normal form, or you continue, and this becomes 2 to the 2 to the 2. This is called hereditary, and this is what we work with. But for my example, I used a smaller number. Know the calculation. The third element is a base change operation. What this means is now I go from this number to 3 to the 3, and I subtract 1. Well, this is not in normal form representation, so I need to write this again as 3 to the 2 times 2 plus 3 times 2 plus 2. And in this way, recursively, we are going to define the Goodstein process sequences. So this is called and G0 is my natural number m. G1 of m becomes this element. G2 of m is now all the bases of the previous element now change to +1. So only the 3's change to 4. And I subtract 1. And this is in the normal form. Next element. And so on. And oh, it's because my computer, I guess, goes to sleeping mode. So this is the Goodstein process, and this is the Goodstein's theorem. So for every natural number, there is a point, gi, where this goes to 0. And it's not immediate because numbers are increasing. Now, there are two elements to check for base change operation. And this is the blueprint, right? So this is our plan that Goodstein has in mind when he goes for stronger theories. So one is monotonicity. What this means is that if two numbers are ordered, then in the base change, which I'm going to define by this operation prime, is less than n prime. So if m is 2 to the 2 and n is 2 to the 2 plus 1, in the base change, this becomes 3 to the 3, and this becomes 3 to the 3 plus 1, so clearly there is a monotonicity of the operation. The other element is the normal form preservation. What this means is that if I have an m written in k normal form, when I change it, the base, the m prime is in k normal form, k plus 1 normal form. Right? And that's why we had to write again the elements in normal form. And this is the first step. Now we have to prove. I mean, why we work with Goodstein principle is because we know that this principle is independent from PA. So how do we get there? So in order to prove termination, we want to be able to associate each element of the Goodstein sequence with an ordinal. And in order to talk about ordinals, we need to give an ordinal assignment to each of these elements. And in order to talk about an ordinal assignment, we need ordinal notation system. Now, for PA, this is quite easy because we have counter-normal forms. And the way that the ordinal, this is ordinal assignment. The way that this works is you take the base in each step to omega. So this becomes omega to the omega. This becomes omega squared times 2 plus omega times 2 plus 2. Becomes 2 plus 1. And as you can clearly see, even though those numbers were getting quite large, the ordinals here are clearly decreasing. And by the well-foundedness of epsilon 0, there cannot be such an infinite sequence of ordinals. So this process has to terminate. So for ordinal assignments, I also have to check. So this is what I needed. We have counter-normal forms, so that was okay. And also here, I need monotonicity. What does this mean? Again, if m is less than n, then the ordinal of m is less than ordinal of n, which for this case means comparing counter-normal forms, which we know how to do. And then is the normal form preservation. What this means is that if m is in a normal form, k of m is in normal form, is in counter-normal form. So this is why we need a notation system. So we need to understand what it means for an ordinal to be. What it means for an ordinal to be in normal form, right? So this is termination, right? We'll have it. Now, these two theorems, the first one by Kirby and Paris in the 80s, they were the ones that actually proved that this process is independent from PA. And this independence from PA is for the hereditary normal forms, and the independence from PRA, later it's for non-hereditary ones. So in the example that we had means writing 16 as 2 to the 4 and stopping there. So how do we prove independence? Well, to prove independence, we need two ingredients. One, we need fundamental sequences. And this usually comes with a notation system. There are different ways of writing defining fundamental sequences. And for counter-normal forms, there are some nice ones which have this property that we need, called Bachmann property. Now, these fundamental sequences, basically what they are is this this canonically increasing sequence of ordinals whose limit is a limit ordinal. So, for example, for successors alpha, I have if I have a successor, fundamental sequence is its predecessor. If I have, say, omega to the omega, then this is omega to the omega x, so omega to x. And if I have omega squared, this is omega times x. Okay? And what this Bachmann property says is that your fundamental sequences are behaving nicely. And why we need this? We need this because of the second ingredient that we need to prove independence. Now, every theory has a proof-theoretic ordinal, and so this is more in the field of ordinal analysis. They assign to theories different ordinals, and what this ordinal means is that what this means is that the theory T does not prove that for each ordinal less than the proof-theoretic ordinal of the theory, stepping down the fundamental sequences actually reaches zero. So the fact that for every ordinal, stepping down the fundamental sequences, so doing these steps, reaches zero, it's a fact. But in different theories, this thing cannot be proved. And this is the associated proof-theoretic ordinal of the theory. And for PA, for example, in this case, I didn't use anything about PA except its proof-theoretic ordinal epsilon zero to show that it's the ordinals below epsilon zero that I'm using to do the mapping. And the fact is that PA itself cannot prove that stepping down the fundamental sequences for epsilon zero is finite. So this is exactly the proof-theoretic ingredient that I use to show independence using this lemma, which in our example it says, take this ordinal here that you assigned to the second element. This one should be bigger, at least as big as omega to the omega k, which case is 2. This is omega squared. So clearly this is bigger. In this case, we have to take this one, so we take omega squared times 2 plus omega times 2 plus 2, k, and it is plus 1. So in this case, it's equal. In this case, we again take this one, omega squared times 2 plus omega times 2 plus 1. In the fundamental sequence is the predecessor, it is this value, and here it's equal. For the last one, we have omega squared times 2 plus omega times 2, 2. This becomes omega plus 2, so this is clearly bigger. So the idea to prove independence is that you need your function of your Goodstein function. This is Goodstein. You need that your Goodstein function is decreasing slower than the fundamental sequences. And this is the ingredient that makes the independence work. And Right. So this was like this is the old school Goodstein from the 80s. So independence here, we had fundamental sequences with Bachmann property. And definition of proof and the proof theoretic ordinal. So what we try to do is to say, okay, so that is a way to write the natural numbers using exponentiation. How about writing numbers that are bigger? And this is where fast-growing functions enter into play. They help us write numbers that are quite big. They grow very fast, for which the elementary operations on numbers might look cumbersome. And this question started a line of work in yeah. So there are quite different fast-growing functions that you can pick from. One of them is the Ackermannian function. And RI with David and Andreas and Weiner, they took the Ackermann function and they went through this whole process. And they showed that these Goodstein sequences, based on this Ackermann function, which was a sort of a complex sandwiching way to write natural numbers, is independent from ATR0. And ATR0 has proof theoretic strength gamma naught. Gamma naught is the limit of the, is the first fixed point of the Veblen hierarchy, for binary Veblen hierarchy. And then later on, we took the Ackermann function and we said, well, is there any calibrations in between from epsilon from PA to ATR0? It's quite a big jump. And we wrote these sort of more intuitive normal forms, and we showed independence from these three systems of second-order arithmetic. Again, the only thing that I use about them is their proof theoretic ordinal. So for ACA, which in reverse mathematics is RCA0 plus the distance of Turing jump, ACA prime is ACA plus for every set X, the nth Turing jump exists for X, and ACA plus is ACA plus for every X, the omega Turing jump exists. And they have different proof theoretic ordinals. So ACA is conservative over PA, so it has proof theoretic strength epsilon 0. The second one has strength epsilon omega, and the third one phi 2 0, which is defined in Veblen form. An example. So this is the Ackermann function that we used. It starts with the exponentiation as a sort of, that would be the intuitive way to start, since for natural numbers we start with exponentiation. And then you do k-folds, and then it becomes more complex. And so this is the notation system for natural numbers, our first point there. So we use that, and then we write normal form representations by picking a maximal A, a maximal B, and leave the remainder in C. And an example of how would a number look for the Ackermann function is this. So if we want to write number 20, we have A to 1 base is 2 there, 1 plus 4. And the way how we got this, the three different calibrations of strength for Ackermannian Goodstein is by rewriting in hereditary form now, again, by rewriting the A or B or C. And this would be a fully written hereditary normal form for number 20. And this would be the third calibration of ACA plus. Right. There are other results in literature. So another attempt was by Rai, Weiner, and Andreas. they used extended Grzegorczyk hierarchy, function f, and they showed that these Goodstein sequences based on this function, they are independent from various theories, from PRA to PA to ATR0 up to ID1. And then another result from David and Andreas is that if we use a Hardy-like hierarchy, the Goodstein process based on this hierarchy is independent from ID1. And ID1 here, which is the first time that we mention it, is Bachmann-Howard ordinal. And in using the psi function, it's written in this form. The question that we ask is, can we go further? So far, we saw that Goodstein had been up to ATR0. These results show that it can go up to ID1. Can we go to ID2 and further? So I mentioned ID1 and ID2. And again, I don't use anything about them. And I can say ID1, I can say Kripke-Platek set theory, I can say pi1 comprehension minus. Like, these are just different, if you want, naming for the ordinals that I'm using. But just for sake of completeness, the theory ID1 is an extension of PA with a new predicate, and this predicate is the least fixed point of a monotone operator. The theory of ID1 is defined as all the axioms of PA plus two more axioms that force this predicate to be the least fixed point. The ID2 is just two iterative inductive definitions. And in second order arithmetic, you can see ID1 as corresponding to pi1 comprehension. And the full pi1 comprehension, it matches with ID less than omega. And as this proof theoretic strength. What minus? Without, yeah. Yeah, light phase, like it's called, yeah. It's called also light phase. Right. So we're talking about these collapsing functions. And before we go there, so what is this Bachmann-Howard ordinal? And what is this collapsing function? So the way that I think about this is you are defining this least set of ordinals, and at the same time you are defining this collapsing function psi. There are different collapsing functions. For example, in the work that we showed before by David and Andreas, they are using the beta function. There are so many other functions in literature, and we use psi function. So I'll show a way of how to construct this psi function. So I will focus on building this Bachmann-Howard ordinal and what does it mean to build it intuitively. You can think of this psi function as mapping uncountable ordinals to countable ordinals. In a way, we had counter-normal forms, we had Veblen hierarchy, and at some point they reach fixed point and they get stuck. So using collapsing function is a way to name more ordinals. Also using the psi function, there are different ways to, like, depending on how fast you want. So the one that I'm building here is the one that we used, and it's not the original one from Buchholz and Schütte, but it's the one that worked for our purposes. So how this works is that I'm going to define psi 0 alpha together with C0 alpha. So C0 alpha contains ordinals that I can build using addition function, the natural numbers, and an external fixed point, an external point, which is capital omega. So the first uncountable ordinal, or small omega 1. So if I have these tools and I'm going to build ordinals with them, I'm going to be able to add natural numbers. So C0 is going to have 5, 11, 14. It's going to have omega plus 2. The first ordinal, the smallest first ordinal that it doesn't contain is little omega. For this reason, psi 0, 0 is little omega. When I go to construct C0, 1, I have all of these terms, and I have also omega. So I do closure under addition, and the smallest ordinal that I cannot access is omega squared. And so on. By this procedure, I build a function that says psi 0 alpha is equal to omega 1 plus alpha. So for alpha, and I continue in this way. Clearly, it's very soon I'm going to reach first fixed point. So when I go to psi 0 epsilon 0, this becomes epsilon 0 because this would be the fixed point of this function. So when I go to epsilon 0, they're here. Now at this point, I try to construct the set for C0 epsilon plus 1. And what happens is that I cannot go beyond epsilon 0 because this is the function that I have, and which means that for a very long time, for a very, very long time, I get stuck at epsilon 0. Now, when I go to construct C0 omega plus 1, something has changed here because now this capital omega was added to every C set. So I am allowed to take it in the construction. So now this becomes epsilon 0 times omega. And so on. At some point, I continue. At some point, I get stuck again. And then I continue, and I get stuck again, and I continue. So it's a step function. And the limit of this is Bachmann-Howard. After this point, my psi0 function becomes useless. I cannot use it anymore. It's going to get stuck in that point. So this is the definition of psi0 function, collapsing function. We use this function to build because in there we said I need a notation system, and so that's what I'm trying to do. I'm trying to build this notation system to deal with ordinals until ID2. And in order, how we do this is first we define C1 and psi1 inductively, and you can think of this function psi1 as after psi0 is stuck at Bachmann-Howard, we can. No problem, we can define a new function, psi1. And how this function is defined is at psi1, 0, you are at capital omega. So the C1, 0 set has all the countable ordinals. The first ordinal that doesn't have the smallest ordinal that doesn't have is capital omega. So that becomes the value. Progressing in that way, you have the second line that psi1 alpha is omega to the plus 1. And the fixed point, if the fixed point for psi0 capital omega was epsilon 0, the fixed point for psi1 omega 2 is epsilon. And So these are the ordinal terms, the sets that we build. And using these terms, we define a system T, which collects all of these terms and defines the less than relation in these ordinals. And this set is not well-founded. And right, so I use all of these C sets and I define a system T and a less than relation. It is not well-founded because it's bringing all of these terms that we constructed. Then I define a system of fundamental sequences in these ordinals. So if it's a successor, it's 4. If it is an uncountable ordinal on the x is x. If it is, so what this means is, if it is, say, psi 0 omega, at x, this x goes inside, so it's psi 0 x. If it is of this form, psi 0 omega at x, so what that says is basically psi 0 omega is epsilon 0, right? At x, this is a tower of omegas. So I need x many. So I need, in a way, to mirror that in the system that I have. And what that says is, if you have psi 0 omega, which is the simplest one, on a value x, what you do is you start with building this sequence of z0, z1, psi 0 omega, 0, psi 0, 0, z2, psi 0 omega, 1, psi 0, psi 0, 0. So this is how, if you can see, this is how I'm mirroring what I intuitively know should be the case. And in the last one, well, if I have psi 0, 2, this is omega to the 3. So psi 0, 2 on value x is psi 0, 1 times x. And so very importantly, this is not the first attempt that we try to do this. And the fundamental sequences here are very delicate. And luckily for us, for me, because Andreas did this, he proved in the 90s that this system of fundamental sequences has the Bachmann property. Because if it doesn't, we have to prove that. And this is what, for example, for theta function, this is what David and Andreas did. So luckily, this system of fundamental sequences that I'm using has the Bachmann property, which allows me to use the proof theoretic facts about ID2. So this is just a technical detail. So I said I built this system T of not well-founded part of from this, I build the system OT, which is the well-founded part, and I do this by basically collecting collecting these coefficients in these sets, and then adding a condition that you are an ordinal in OT only if this condition holds. As an example, in OT, you have an ordinal such as psi 0 omega, but this one is not allowed here. That ordinal makes it that you can have a descending sequence and an infinite descending sequence in T. And we want to work in OT. That's why it's very important to extract Right. So now we go back to the beginning. So what we did so far is we built this notation system. This is the only thing we did. And so this was the work we did so far. Now I need to go and define normal forms from natural numbers. So what I want to do is I want to use this Hardy-like hierarchy to write natural numbers. And well, it doesn't look like the usual Hardy, but this is what works for us. And this is the only unusual case. So what that says is basically if you have an Hardy function indexed on an ordinal, say omega, then this is equal to h omega k, okay, which means h omega fundamental sequence, h omega k minus 1. So what this curly brackets is doing, it's building these layers of nested Hardy function. And just like a very interesting thing. So you see that nesting, doesn't it look similar to the thing that we're doing here? So that is where these two things connect. So as you go forward, you see how does Hardy hierarchy behave, and how do my fundamental sequences behave, and can this match? We define normal forms. So for the normal forms, first we pick a maximal alpha, such as this holds. Then we either put the rest in a Q, or if Q is bigger than this component, we count the number of and this is the final K normal form. So here we have an ordinal which is less than Bachmann-Howard ordinal. So this L as well, it's just probably a remainder, a number that can also be written using the Hardy function. And P is a constant less than K, and Q here is also written using the Hardy function. I have to define base change operation. So so this is just a shortcut for the ordinals that we are using. So this is the set of ordinals that I'm using to index H here. So I had that M is equal to H alpha K times P plus Q. And this alpha here, it's coming from this. I define base change operation, not in P, everywhere else. I define base change operation for ordinals. So everywhere where an ordinal has a number, it changes. Very crucially, so we said that we were in this system OT. And I mean, the alpha here was in OT0, so even more constricted than OT. When we do this base change operation, the ordinals are not guaranteed to be well-founded. So what happens is that when I have to go and check for monotonicity and normal form preservation under base change, I need some properties about these ordinals that I'm using. And this, I define the Goodstein process as before. So this is exactly as in the base case. So when I have to prove this monotonicity and normal form preservation, I need some properties about these ordinals, and we define this this notion of ordinal context and think of it as a sliding window to your ordinals, and it stops exactly where these ordinals are changing. So before it was easy to see that, okay, the ordinal where m has map 2 is smaller than the other ordinal, but in this case, the ordinals are much more complex, and I need a very delicate sliding window to see where these ordinals are changing, and to say something about these ordinals. So, for example, in this easiest case, what does it mean for two ordinals to be less than another one? Well, if alpha is something plus psi 0 t, and beta is plus something else, and beta is psi 0 omega, how can I guarantee that these two ordinals that alpha is less than beta, even though it has another part? Well, this t has to be less than beta at fundamental sequence t plus 1. So what I'm doing is I'm setting a bound on b. More conditions. And in order to prove monotonicity, I use these lemmas about the ordinals. So I say, if alpha is maximal in my normal form, it has nice properties. If it has nice properties, then if it has these nice properties, which I prove here, then I can be able to say that h alpha plus 1 of k is less than equal to h. So I'm able to say something about the difference between normal forms where they have different ordinals. And it is exactly these two lemmas that I move to the realm of base change operation, and I use them to show that actually the base change operation is monotone and normal form preserving. And after I do this work, I show that actually the base change operation is well-founded. So it is so the normal forms are in Buchholz's normal form. The normal forms after base change operation. Now I want to prove termination. So in order to prove termination, we said that we need an ordinal assignment. And this ordinal assignment now, if it's operating like this. So if I have so m is an age function, right? This m is moving to psi 0. And psi 0 is moving to psi 1. And psi 1 . So this is what the ordinal assignment is doing. P still remains a constant, so I don't change it. And this is the two second lines are the extension of the ordinal mappings for. Now, we again come here to the same problem. So this ordinal assignment is mapping natural numbers from k normal forms to ordinals which are not necessarily well-founded. And I still need to check monotonicity and normal form preservation to show that actually the ordinal assignment gives me ordinals that are well-founded. And for monotonicity, this is easier in this case than for base change operation. Normal form preservation under ordinal assignment, it's directly using the properties that we built in the notation system. So what does it mean for this ordinal to be in OT? What does it mean for this to be in OT? This is where this G sets that we had defined in order to regulate the ordinals that we were using, they come into play. And we have to show basically the property that we built into the system OT, which is you are an ordinal in OT only if and only if the G0 of your argument is less than the argument. I mean, we can make an example, like we had this, which we said it shouldn't be allowed in OT. So T0 of psi 0 omega is equal to the argument itself, psi 0 omega, union G0 of psi 0 omega equals to, and this thing is not smaller than the argument. That's why this ordinal cannot be in OT. And this is what we need to check. We need to check that while we were mapping ordinals, did we map into anything that shouldn't be allowed? And then we show that well, actually, if M is in K-normal form, then also this OKM is in OT, is in normal form for the notation system. And as a corollary, we can obtain that the ordinal assignment is and combination, then it's almost as an observation, just like we did in the base case. In order to prove independence, we needed this. This is exactly the same lemma we had for Goodstein in PA. So what we said for Goodstein in PA is I need that my Goodstein sequence decreases slower than the fundamental sequences. So if these are the fundamental sequences that I have for ID2, and I have already defined an ordinal mapping for my Goodstein operation, I need to check that this is the case. And I will, since we have time, I'll give just one case to how this is done. So say that M is equal to H omega K. And I need to check that. OK plus 1 of H omega K plus 1. So this is M prime minus 1 is bigger or equal to H OK of H omega K. Thank you. This is what I need to show. And so this lemma, that lemma there, it's done for every single case and every single option that you have to write your normal form. And you need to check this for every single one. And if one of them fails, you have to go back and define your notation system again from the beginning. So how does it behave in this case? So we start from here. This is equal to OK plus 1 of H. Well, first of all, I cannot apply the ordinal assignment because this is not in normal form. So first I need to bring it in normal form. So this is curly brackets here, K plus 1, K plus 1, minus 1. I need to get rid of that minus 1 somehow. So I say, well, that is as good as H omega K plus 1. Actually, that is bigger. So I can use this one, and I can apply the ordinal assignment here. How does this look like? Well, this is, I mean, not to be confused here, let me just rewrite this. What this K meant was H omega K minus 1. So what this is a psi 0 term, because I'm sending a natural number to psi 0. Psi 0. Now this is OK plus 1 of, I mean, here you can delete this. H omega K minus 1. Psi 0 of. Now, again here, this was layering of H of. And I have 0, 0, 0. How many many times? K times. Right. Okay. Now let's see if this is how about this one? So here I have this. So OK of age omega k is psi 0 of omega. Because small omega goes to big omega. Now, we gave this example in the beginning. What does this look like? This looks like a psi 0, k many. And amazing, they are equal. So in this case, it works. And it also works in the other cases, of course, which allows us to use the proof theoretic property that ID2 doesn't prove, that stepping down the fundamental sequence for the ordinal of ID2, which is using our notation system psi 0 of psi 1 of epsilon omega 2 plus 1. Terminates. So this gives us independence.